Partial sums of geometric series. Previously, we talked about the infinite sum. And it's weird that we're going from infinite stuff to finite stuff. That you'd think that finite stuff would be easier, but we're going to use the infinite stuff to prove the finite stuff. So recall that the sum from 0 to infinity of a sub 0 r to the I is a sub 0 over 1 minus r. So what does it mean if we go a sub 0 r to the I from 0 to n? So the difference between these two expressions, it's important, is the infinity versus something that's not infinity. Here we're adding up a list that ends at some point. How can we do that quickly? So the big breakthrough is realizing that if we're adding up a geometric series, it looks like this. A plus AR plus AR squared plus AR cubed, etc., all the way up to A times R to the n minus 1. And that can be written as an interesting subtraction. If we continue this pattern, this is the whole infinite series, A plus AR squared plus AR cubed, etc., and it just keeps going. Minus, well, we want to cancel out these. Those are not part of our original expression. These would cancel out, these would cancel out, these would cancel out, etc., and we'll just be left with what we had in the first place. So this is the big breakthrough. That this, in here, in green, that represents our infinite sum. This is A times 1 plus r squared, and then it continues infinitely. I use the dots that don't have some endpoint to represent that it's infinite, whereas these dots that have something after them represent that it is finite. Now, this part is similar, except they're all divided by a and r to the n. So this is a times r to the n, and then what we're left with is 1 plus r squared plus r cubed, etc. So now we have a greatest common factor. Both of these are divisible by that infinite sum. So we can write this as a minus ar to the n times the infinite sum by factoring. Then this part, we learned a formula for that. That's 1 over 1 minus r. And this is a minus a times r to the n. Factoring an a out of this gives us a times 1 minus r to the n over 1 minus r. And this is our formula that we will be using. The partial sum, the nth partial sum of a geometric sequence with first term a sub 1 and common ratio r is given by, there's something missing, this whole thing times a sub 1. Note that r cannot be equal to 1 in this formula, otherwise we'll get 0 divided by 0, and that doesn't end up well. But as long as r is not equal to 1, this will work, even if r is greater than 1. So let's find this sum. So our sum is a sub 1 times 1 minus r to the n over 1 minus r. A sub 1 is our 3. R, well, we're taking negative 6 and dividing by 3. Negative 6 divided by 3 gives us negative 2, which is r. So minus negative 2, watch for the parentheses, to the nth. How many are there? 1, 2, 3, 4, 5, 6. Over 1 minus negative 2. And now we simplify. 3 times 1 minus negative 2 to the 6th is 64. And now this becomes, the 3's cancel, and we get 1 minus 64 is negative 63. So, again, what we need in order to do this is we need our first term, whatever the first term is, which will sometimes be a sub 1, sometimes be a sub 0. Whatever our common ratio is. And we also need how many terms there are. So how many terms there are? It's 7 minus 1 plus 1 is 7. Common ratio is 5. 5 is what's being raised to the ith power. And our first term is when I is 1, so that's 5 to the first, or 5. So the sum is 5 a sub 1 times 1 minus 5r to the 7th over 1 minus 5. Now, 1 minus 5 to the 7th, you'll still want to do in a calculator. So 1 minus 5 to the 7th, I'm getting 5 times negative 78,124 over negative 4. So divide that by negative 4 and multiply by 5, and I'm going to get that that is equal to 97,655. If you don't believe me, add 5 plus 25 plus 125, etc. to up to 5 to the 7th. Find this sum. So we have a sub 1. Our first value is when this is 1. We have 1 minus 1 is 0. Let me do it out. Negative 2 times negative 4 to the 1 minus 1, negative 2 times negative 4 to the 0th, negative 2 times 1, negative 2. Our common ratio is clearly negative 4, and n is 7. So we have negative 2 times 1 minus negative 4 to the 7th over 1 minus negative 4. Negative 2 times negative 4 to the 7th. So 4 to the 7th is 16,384. And when we raise a negative number to an odd exponent, it stays negative. So now we have negative 2. We add the 1 in the numerator, so 16,385 over 5, all times 2, gives 6,554. Find the ninth partial sum of a geometric series with common ratio negative 2 and the first term 1. Now we don't have to write this out, but I'm going to show you the way that I would write this if I wanted to write it out this way. It's from the first term to 9. The first term is going to be 1, and the common ratio is negative 2. We need to make sure that the exponent works out so that the first term is still 1. So I minus 1 will mean that when we plug in 1, we'll get out 0 for the first term. Or sorry, 0 is the exponent so that the first term is 1. We have everything listed out here, so I'm going to need to rewrite it. S is 1 times 1 minus negative 2 to the 9th over 1 minus negative 2. 1 plus 2 to the 9th is 512. Negative 2 to the 9th is negative 512 and minus a negative. And then we have over 3, so we have 513. Did I do that correctly? Yeah, 513 divided by 3 gives us 171. Lastly, the number 4 is repeatedly multiplied by 2 until the number 1024 is reached. Then each of these numbers is added up. What is the total? So the interesting piece of information that's missing here is how many times are we multiplying by 2 to get to 1024? Now, there are a number of ways to do this. The fastest way, in general, is, I believe, to take log base 2 of 1024 divided by 4. So log base 2 of, this is 256. And if we take log base 2 of that, we get 8. So that's one way of figuring out how many times we're multiplying. Or, and that's how many times we're multiplying, which means we need to add 1 in order to figure out how many numbers are being multiplied, or will be added. So n equals 9. Or you could continue this process and say, well, we have 128, then 256, then 512, and then 1024. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Either way will work. So 1 plus might be the formula that you may want to memorize. 1 plus log base, whatever that number is, of our final number divided by the original number. Then each of them is added up. So that's why we're finding a series. We will say a sub 1 is 4. 1 minus 2 to the 9th over 1 minus 2. So 4. 2 to the 9th is 512 over negative 1. So this is 4 times negative 511 over negative 1 equals 2044. Thanks.